Hey everyone, thanks so much for joining us back from the break. I hope you're able to stretch your legs and get some coffee. I'm Paul McLaughlin. I'll be presenting our next speaker, who is Angie Liu, who's a postdoctoral researcher at Caltech. And she'll be presenting machine learning for the real world, distributionally robust extrapolation. Thanks so much, Angie. And I will give you a 10-minute warning and a 5-minute warning, just so you have that in chat. Thanks so much.
Cool. Good afternoon, everyone. Today I'm excited to tell you something about machine learning for the real world, distributional robust extrapolation. I'm Angie Liu. I'm a postdoc researcher at Caltech. This is a collaboration with several amazing colleagues, which is shown here. So let's look at some examples of real-world machine learning tasks. So biologists may want to use machine learning for fine-grained species classifications. However, they still cannot get very satisfactory accuracies on some classes that has very little data. Also, doctors want to do disease detection based on images. However, they cannot really trust our machine learning models in many cases. Also, control experts want to use machine learning to model some of the very complicated aerodynamics dynamics in control system. And also social scientists, they want to use machine learning for hate speech detection and also building a more trustworthy social media, which is what we really want, what we really need right now. However, these are very good and very important applications, but we cannot really achieve our satisfactory performance there. So why is it in the real cases? Let's look at how we usually train our machine learning models. So usually we will make sure our training data and testing data look the same. And the way we do it is like we collect some data and just shuffle them randomly. And we know, like, theory tells us if the data is large enough, there's some generalization bounds due to concentration inequalities. So that means if the training and testing are similar enough, we can guarantee our performance on test data. However, this is just not how the real world is working. For example, if you want to do species detection in Africa, but usually the data is limited there. So you only have data maybe labeled from America, then there's this domain shift. And also in the control cases, you have maybe some training models trained in the clean lab when there's no rain, no wind, no snow, no disturbances. But then when you deploy in the real world, there are this wind and disturbances you can never mimic in the lab. Or you may have some models working for hovering, like the drone can use your model to hover in the space, but cannot really use this model for landing because there's very complicated interactions between the device and the ground or some surfaces. So exploration can be regarded as a domain shift problem. For example, if we want to put a mouse rover to the space or to the inner Mars, then there's some historical data it sees before. So the state space in the historical data it is familiar with. However, there's a whole lot of space that it cannot really see before in the historical data. Also, what makes things very tricky is there can be a space in your state space that the mouse rover cannot really touch because they're just so dangerous and that violate your physical limits, and it will break our very expensive devices. So this is the problem that says if we ignore the distribution shift, ignore the data shifts here, it can be very risky. So what will be the right model extrapolation strategy when we are in this safety critical application? So for example, in this very simple regression problem, we have some blue dots as training data. And then if we only depend on this training data and then blindly extrapolate the model using this linear model, you will see there's a big gap between this prediction and the ground truth, which is the red curve. So what should be the right extrapolation strategy using our historical data when we are in this very high stack applications and also safety critical applications? So there are two choices we are presenting here. One is the left-hand side. Let's imagine there's a classification problem. We have some plots and circles in 2D domain. There's training data that's shown in the plot, and also this, let's say it's a kind of Gaussian distribution that's in the right tilted angle. And then the testing data is this right tilted distribution Gaussian, which you do not really see the testing examples here, but only see like the space.
Angie, I'm so sorry to jump in. In your audio quality, and it's a bit hard to hear your voice. I don't know if it's just me, but maybe others may be having a hard time hearing your voice.
Let's move in closer. Is it better now?
Yes, it is.
So, okay, I moved it closer, and then let's see what it is. So in this left-hand corner and the right-hand corner, when there's no any training data, this model is extrapolating very optimistically. That's saying the red and blue means like you're very confident. The deep red and deep blue means that you're close to like very certain about it's a plus or it's a circle. Well, in the right-hand side, its examples tell you that, oh, in this region, when there's not much training data, I will just say I'm not really sure, because the green color means the prediction is close to 0.5 or close to the middle range of the model confidence. So that means when there's no data, I try to be conservative and then try to not extrapolate too much from my historical data. So we think this kind of extrapolation maybe is more useful and more is more useful for these safety critical regions, because it just will extrapolate from data more conservatively and to be more honest with our data. So our goal here is trying to enable machine learning models to be aware of distribution shift and extrapolate accordingly, such that it can be integrated into real-world systems to satisfy safety critical requirements. Let's look at this example, which we will use as a running example in our talk today, which is drone dynamics learning. In drone dynamics learning, assuming what our problem is like, given the position, velocity, and orientation of a drone, we want to predict what's the aerodynamics, which is the ground effect when it's interacting with the surface. So the X input is like position, velocity, and the orientation of the drone, and output will be the force that it will experience during the interaction with the ground. And this ground truth model, physics, which is based on physics, we know it's like unchanged, even you have slow or fast speed. However, we may only have like slow landing data, but do not have the fast landing data to which is hard to collect with a human pilot. So the input data distribution changes while the ground truth physics model is still unchanged. So this is a special distribution shift assumption, which is called covariance shift. Using this as a running example, we want to reason how can we get to this conservative extrapolation instead of this very aggressive and optimistic extrapolation. So this is our roadmap today. We'll first introduce some classic tools from adversarial estimation or distribution robust learning. And then we'll see how it will work in the distribution shift case. And then we'll see how we integrate it into the real world systems. So first, some background. So there are mainly two approaches of machine learning. The first one is called empirical risk minimization, which maybe is very familiar with everyone. Usually you have the estimator that have direct access to your training data. And then the goal is to minimize some loss function in this empirical distribution of data, which will assume our data is mimicking. The other way to think about it is called distributional robustness, which is like we do not assume the estimator has direct access to our training data. Instead, it has access to an adversary who is constrained by our training data. And there exists a game, a two-player game or minimax game between this adversary and estimator. And the adversary cannot be too freely, so you still need to be constrained by training data. But then the whole idea is that estimator do not have access to this training data. And when they achieve this equilibrium, we assume we will get this distributional robustness. So when there's no distribution shift, we can formulate this kind of game. So we have estimator player P and our adversary player Q. So the estimator player trying to minimize our loss function, while this adversarial constrained by our training data is trying to maximize the loss function under some constraints. And this constraints is according to some training data distribution. And also the loss function is also defined on our training data distribution. They are the same distribution, so there's no distribution shift. So what's constraining our adversary is exactly the same thing that's defining our loss function. So the definition of robustness here is like the estimator try to achieve its best payoff or some equilibrium. If you think of it as just game theory, and then the payoff is just our loss function, then the estimator try to achieve the best payoff or equilibrium when playing this game with adversary. And this adversary needs to be compatible with the training data. So this is the notion of robustness in distributional robustness. And let's see what happens on the distribution shift. So on the distribution shift, we still have this game between adversary and the predictor, but the difference is like we do not have any labeled target. So on the distribution shift, we have some labeled source. For example, you have slow landing data or slow flying data, and with the ground truth aerodynamics. Well, you do not have the fast landing distribution when, and it's hard to really measure the aerodynamics when it's very fast, right? So the unlabeled target. So the adversary is constrained by this labeled source data, but then the game is still, so that means our, what we are interested in is still on this target distribution. So there is this shift between labeled source data and also unlabeled target data. The game is on target while the data is on source. So under this distribution shift, we will have this kind of game, which is similar as before. We still have a minimax game. We have two players, P and Q. P trying to minimize the loss function, Q tries to maximize loss function. The difference is like loss function we are interested in is defined on a target. Well, the data we have is only training, is only like source, which is different from our target. So there are two differences between this model and the previous one. One is like you have the target distribution as your interest. The other one is like you need to constrain the model, constrain the adversary more carefully. As an example to see how this actually shows, as shown in the 2D example, we see this two Gaussians. Still, we'll imagine there's a classification problem here. So the source data we assume is a very restrictive small Gaussian with very small variance, and the target distribution we assume is larger, is the same mean but larger variance, which is like broader distribution. And then we can see that in the right-hand side, this is our model prediction. The color map is the confidence on how confident I think this is a positive or it's a circle given the position. And then only in the like very restricted region that you have source data support, you will have this more confident plus or circle prediction, which is the blue and the red color. While outside in this region, you will be very conservative, which is you make prediction that's around 0.6 or 0.5, which is like you're not confident about your prediction. So we think this way, we instead of extrapolating very aggressively, we are being honest to data. But also it's a very quite pessimistic and conservative perspective. So the takeaway here is like we give uncertain prediction on data samples that's quite far away from our training data, unless being told now to, given prior knowledge by the user. So if we have prior knowledge that says, oh, I still want to be very confident outside of this region, we need to engineer our constraints for the adversary to be able to extrapolate more aggressively. Otherwise, this model will just be very pessimistic about data. Okay, let's see how it works in the real world. Our task here is this control drone to land, but then we want to say, how can we land fast but also safely? There are three ways of landing a drone. We can do, for example, slow landing and safe. So in this plot, the blue curve is like you touch the ground with velocity 0, but then you still, the time is like much longer than the other two. And for the orange and the green fast landing one, the orange one is still safe, which means I touch the ground with velocity 0, but then I use a much short time. And also still being safe when I touch the ground. It means like I do not have a large speed when I touch the ground. And the green line means like, oh, I touch the ground with this kind of high speed. And then I use much less time, but the velocity is very high when I touch the ground. So what we want to achieve is like, can we do fast landing but safely, which is achieving the orange line. So we want the machines to extrapolate and also explore the space by itself. So it's still going back to our previous example of Mars rover. The drone is in a similar situation. So assuming you have some data that's doing slower landing and do not know how to do fast landing, then from slow landing to fast landing, this kind of extrapolation actually just enlarge your state space. And then you still have a space in your state space that it cannot really touch, which is a dangerous region. In this case, which is like this. If you touch the ground with a very fast speed, then you have the danger to break your device. But we design our safe exploration framework like this. So similar as the right-hand side is the learning, which is we use our distributional robust model, as we shown before. We have adversary and estimator play a two-player min-max game, and we also have feature constraints from some data. However, this data is a dynamic one; it's not a static one at all. So every time we get some worst-case error bound from our model, we will try to select some data from trajectory pool, and then check the safety. And then if they are safe under the worst-case possible model, then we will use controller to crack data and then add this data to source. And this source will constrain again, constrain this adversary. So this is an iterative process. With more and more data and with better and better model, the bounds should be tighter and tighter. So you can imagine at the beginning, you have only maybe one data point. Then your model is very, very conservative. So you will not be able to extrapolate a lot from the model. So when you choose your trajectory pool, you'll choose also very conservative trajectory, a slower one. But after you get more and more data, your model is modeling the dynamics better and better. You are more aggressive in your model extrapolation. Then you can choose a trajectory that is faster to query and then to execute. So here we use a very standard feedback linearization controller, and also use a simulator that is based on real-world data to simulate the process. So let's look at how it works in the simulator. So in epoch 1, without any data, we're very conservative. So what will happen is the drone will land, but then it will hover at some height. So in this 10 seconds, it is safe all the time, which is if you do not really touch the ground, right? But then it's always like hovering there and never lands. After 10 epochs landing, we will achieve a faster landing, which is the drone can land and also with a very fast speed. And also at the same time, it will stay away from this unsafe region, which is when the when the velocity at the end is like larger than 1 meter per second. And usually in our experiment, we convert to the fastest landing in 10 to 15 epochs. We also experiment another simulation, which is in our spacecraft and spacecraft assembly and simulation facility in Caltech. This problem is called spacecraft docking. So assuming there are some obstacles in the space, and the spacecraft try to explore the space as much as possible, trying to getting from A to B, which is like this end to this end. We have some parameters trying to control like how important the exploration is, and then when rho is like 0, it's just optimize only the fuel cost, which is like I want to use as less fuel as possible. When rho is equal to 1, it means I want to explore the space a little bit more, but I also stay away from the obstacles. So we can see that there are 3 trajectories here. One is the nominal one, which is like if you know the true model, ground truth model, then you can do a fast trajectory and then stay close to the obstacle, and then but still being safe. Since we do not have a perfect model, we're learning the model. We're not as good as nominal model, and also when there's different rho parameters, we'll have different behavior. In the red trajectory, the spacecraft will do is a curvy one, which it will collect data that has a much larger variance than this blue one, which stays closer to the obstacle, and saves more fuel. But in exploration mode, it can go larger, have a larger space in exploration, and stay a little bit far away from the obstacle, but also stay safe in the whole process. Also, in the right-hand side, we compare if we do not have the safety consideration, which is this pink line. It will actually, if we just do feedback controller, it will actually collide with the obstacle here. So in our approach has 30% higher success rate than standard planning algorithm in epoch 1. Finally, we can also look at some analysis on the how learning is improving the uncertainty and the convergence rate. So with more and more learning epochs, we can see that cost just dramatically goes down. So you get a better model, then you can have better control, have a better controller. And also, if you look at the variance in the planning, you can see that it also goes down dramatically. The number of collision in the simulation also goes down dramatically. So if we have a better learning model and also this conservative extrapolation, we can stay safe, but also have this huge improvement in both learning performances and cost performance. So as a summarization, we talk about distribution shift is inherent in many real-world applications. And then we talk about there's a way called distribution robust learning that accounts for the worst case model. If you have this two-player game, then we assume that the adversary is constrained by the model, and then we can achieve some worst case performance. We can achieve the robustness against worst case performance. And then we look at conservative extrapolation as examples in both 2D and also in the real world cases. If we do this conservative extrapolation, it can enable this kind of safe operation. So the drone and spacecraft can collect data themselves, learn without any human pilot in the loop, and then explore the space also safely. And then we try to apply it to real world systems. Even though the examples I give today is still in simulation, we're working with control expert to deploy it to the real world. As the outlook, I want to ask this question, like, will you build an airplane that is powered by machine learning? So I guess if we do not have this worst case guarantees and this worst case robustness guarantees, it's really hard to answer this question and really hard to trust our system. But I think if distribution robustness is kind of the promising direction that can give us some opportunities to have more trust in the machine learning model. Also, predictive performance is not the whole story. I think in the talk today, we listened to the previous talk, which is about interpretability, and I talk about safety, and there are other principles like fairness and calibrated uncertainties we need to consider. Because, for example, in the healthcare case, doctors will just not trust the model if you cannot really explain and do not have the right amount of confidence. And I think deal with distribution shift in a robust way is a promising direction. And in other part of my research, I also look at constraint satisfaction and calibrated uncertainty and social impact AI. And I think if we have fundamental models that can give distributional robustness, then there's a hope that we can apply those models to real-world applications to achieve the trust of machine learning models. Thank you. And I'd like to take any questions.
Great, thank you so much for a fascinating presentation. If you have any questions for our speaker, please put them in the chat and I will happily read them for Angie. If not, I might ask you a question actually based on your hypothetical around the airplane. What would you want to see or have in place before you boarded a plane essentially guided by machine learning and to build on the hypothetical you asked?
Yeah, I think I really think I'm a person from machine learning theory, and I do really want to see we have special guarantees for the models we apply to the, for example, airplanes or any safety critical, for example, control system, right? So if we know this model with enough data, this model is have the worst case robustness guarantee, then I'm kind of assured that this is going to work at least if everything else works out. But also data limitation is also one thing. So we cannot always assume that we have the right amount of data. We have for example, deep learning models. They are just data handling. So we also need to have the right data pipeline for those applications. So algorithm is just one thing, theory is one thing, but also implementation and engineering is also another thing that can affect the result of that. So I guess distributed robustness is one promising area that in the algorithm side, but then I think before that's coming to, we will need to work with engineers, machine learning, also theory, and also the pipeline engineers to make sure the data there is working okay, and then other engineering part is working okay. So I guess it's a very collaborative effort.
Absolutely. So it looks like Lee has a question. Move it, unfortunately, just says, there we are. Is there an architectural difference between your model and GAN models?
So that's a good question. GAN is also a model that uses minimax games. But then difference is our model tries to solve this game just explicitly, while in GAN's case, usually do not or cannot really able to say, I find this equilibrium. And maybe in GAN's case, they do not really need to find the equilibrium because you're just doing image generation. But in our case, we really trying to find this equilibrium, and that will give us this worst case robustness. And also there are certain loss function that's easier for this finding this equilibrium. Well, in GAN's case, if you have two network and your network, which is very complicated. So I guess the difference is first we find this equilibrium just exactly, and the second is we're still working on trying to make sure for different or very hard to optimize loss functions, we can still do that. And then I think that's the key, key difference between our model and GAN. But I think GAN is definitely in a very similar track with this model as well.
Well, I think that will actually take us right to on time. Thank you so much, Angie, for your presentation.